All right, how you guys doing? So I've got just a couple quick small updates to the syllabus for you to highlight, kind of just also talk about where we are. Um, do you guys have a good break? Nice. Anything fun, interesting? Not too much, just a little less intense. Yeah, same for me. I did a little bit of work, got caught up a little bit on stuff, but also on some sleep and all that. All right, so now that we're back, we're going to talk about disinfection today. Mostly ultraviolet light. This is really getting into my specialty. We'll probably next time just dive into sort of research topics kind of stuff, my fun stuff. Today we'll cover kind of the rest of what we need in terms of connecting disinfection principles to rate constants and deriving stuff like that. Maybe I'll touch on one more sort of core technical topic next time, but I think it'll mostly just be giving you an idea for what kind of innovative technologies are around for disinfection. Then after that, I've moved the intro to wastewater segment. Of course, as you know, most of the stuff that we've been talking about does deal with wastewater also. But that's the point where I normally would put that after the second exam and really launch us into strictly wastewater topics. However, I needed to move some things around because on November 7th, so the class period after our exam, I have to have an all-day meeting, and even if I'm on campus, I won't be able to lecture. So what I'm gonna do there is move what was going to be my seminar on the Flint water crisis. So I was actually living in Michigan for 2 years right around that time. So I have some personal experience, some firsthand knowledge or secondhand knowledge of some of what was going on there. So instead of providing you that lecture here, I will give you one of two options. One would be to listen to a lecture by a professor who was working on the issues there. He's from Virginia Tech, has dealt a lot with lead and water issues, a lot more specific to that particular problem. He'd worked in DC on some projects, and at that time was a professor. I was not during that time. So I was not involved academically, and perhaps thankfully. So he gives a really nice kind of high-level presentation on that. Of course, I also typically give a lecture in this class every time I teach it. So we've got plenty of recordings. So I'll give you the option to listen to one or the other. So I'll post those, or you could do both if you really find it interesting. There's going to be some sort of Moodle quiz. I think either way, you should be pretty well prepared for it. It's kind of participation activity on it for the core issues that were present. So I will post that in some old notes from my slides. I think my slides go a little more into the health impacts of sort of some of the related stuff. There's a corresponding Legionnaire's disease outbreak and some surveillance investigation on the public health side for that I had some exposure to. So I'll post those resources for you, and it'll be a free period otherwise. So kind of like do it at home sort of a lecture for that one. Otherwise, I think we're pretty well on track. So we'll do an exam review, cover the homework solutions on Halloween in preparation for the second exam. All right. Any questions, concerns, or anything for that? All right. Last time we left off saying we would take a look at this particular problem for kind of practice looking at some data that we might get from a disinfection experiment and saying, okay, well, what can we learn about the rate constants in this particular scenario? And again, this is just a little more practice on our mass balance systems, except with the flavor of dealing with a chemical disinfectant. And so the thing that we're adding here is that disinfectant, and using the Chick-Watson kinetics that says we have a constant concentration of disinfectant And that multiplied by this specific rate constant between a disinfectant and a pathogen gives us a new constant that's K star that does essentially what we've been using K for the whole time. So let's take a look at this problem. I think we'll need a little bit of Excel here, but you could do it on a graphing calculator with no problem. And I'll give you a few minutes to think about how to approach this and work with it. So it says the data for HOCl disinfection, that's hypochlorous acid, that's free chlorine, of poliovirus at a concentration of 1.8 milligrams per liter, that's our chlorine, is shown below. The temperature was 20 degrees Celsius. That, if we cared to, we could change the equilibrium constant a little bit. We're not going to. We're going to assume that the Ka for chlorine is 10 to the negative 7.54. Would be very close to that at 20 Celsius. The pH was 6, and it says determine the rate constant for inactivation, assuming Chick-Watson model applies with an n value of 1. So the Chick-Watson model is essentially saying that dn dt is going to be equal to negative k times c to the n power. Those are our constants, times n first order to the 1 power. Okay, and so this data here is collected. It doesn't give us much information, so I think it's safe to assume this would be in a little batch container, in a petri dish or something, a beaker, to test it, and we gather some data from it. Okay, so the task here is to go from the data to the rate constant. So give it a little bit of thought. I'm going to pull up what it might look like in Excel. If you've got a graphing calculator or Excel, or just do it by hand, you can actually do a pretty good job aiming to get there. So give this some thought. I'll let you have a few minutes to do that. One thing you'll see in this problem is that we're given some information that we could use to find the equilibrium value of HOCl, to see specifically how much is HOCl. At pH 6, it's mostly going to be HOCl. There's going to be a little bit of OCl minus if we remember that equilibrium chemistry. So we'll just assume you could calculate this, and I think I have that in my Excel probably, but let's make the assumption, to simplify things a bit, that about all chlorine is HOCl. And just to explain, it would normally be some mixture of HOCl and OCl minus. Oops. Right. So I'm taking the chemistry out of it for you. All right. You guys feel like you have an answer, or at least got far enough to get stuck? Something like? I know one of you that has done a lot of this for me with some research some time ago, so could pick on you and get that answer. But okay, so the approach here would be to take a line of best fit, which is not what I just drew. In order to solve using the data to get our kinetics here, we can take a line of best fit if we set it up properly in the form of y equals mx plus b, right? And if we look at what we have, we could graph it just as it is, like the number concentration over time, but that's going to give us kind of an exponential plot, and that's not so great for lines of best fit and all that. So if we transform that into this natural log form, and by the way, we could leave it as n equals n naught times e to the negative kt or kct, either way we want to write it. We could leave it that way, and that's this plot at the bottom left there. But if we transform it and simplify it in doing so, we can take the natural log of the n divided by the initial n. And for every value of time, get a new data point that is transformed in that manner, because we have that data, n at some time t divided by n at time 0, and take the natural log of that. That puts it all in the form of, instead of n equals n naught and all that, we're leaving it in the form of this ln of n over n naught is equal to minus kct. That is essentially y equals mx plus 0. Okay, and we have a plus 0 there, which is very nice, so we don't even have to think about that. So we'll say y equals mx, where m is our k star, and x is time. So, and in this case, y is the natural log of n over n naught. So in that way, we can plot it, find the line of best fit, and ultimately derive our equation. Okay, so let's see what that might look like in Excel. Maybe. What'd I do? Okay. All right. So I put the time here, the number concentration here, and I went ahead and took the concentration times the time. You don't have to do that. You could plot the x-axis instead of time as the concentration times time. It's not necessary. We can account for it before or after. Then I took the natural log of the n over n naught. So if we look at the equation, the first one is just that 6,152 divided by itself, which is going to be 1, right? But then the natural log of 1 is 0. So anything to the power of 0 is 1. So that first value is 0, which is why on the graph, I went ahead. I'm not writing anything exact here, but I know it would start there at 0 because that first value has to be. So, and then we expect something like this where this slope is m. Okay, so then we solve each one of these components. We see it's the current n divided by the initial and go down the line, and then we can plot that as the natural log of n over n naught versus time, which looks like this. We get a nice regression there with a nice slope. We don't have to worry about the plus b because there shouldn't be. It should pass straight through 0, and I can force that. And there we have it, y equals negative 0.3758x. So our k star then is that negative 3.57 blah, 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 blah. Okay, so that's our k star, and then we have to divide by the chlorine concentration to get the raw k value, and we're done. If we wanted to be fancy, we could take the concentration times the time, and then this should also go through 0. I should correct that. And then we don't have to divide by the concentration because we already put that into the x value. But that's just being fancy. Don't worry about that. So we can take that negative 3.758. Negative. Three, 5, 7, 8. 3, 7, 5, 8. And if you notice earlier, I put the K units here, the K units are a little funny because the K is also accounting for the chlorine concentration. The K star units are not so funny. They're like what we've normally been doing. So this should be per seconds. Seconds to the -1. So when we find the answer to the question, what is K, that's going to be K star divided by the concentration, which is why ultimately the units are going to be a little different. And so we just need to take that. Maybe I've done it. Guess not. So if K star equals 0.3758 and the chlorine concentration is equal to 1.8 milligrams per liter, then K should be K star divided by that K, and our units are going to be liters per milligram seconds. So final answer there should be negative 0.209. And these will be the funny units, liters per milligram second. Okay, does that make sense? So I wanted to demonstrate this to kind of walk you through how we can go from something in the lab or something practical that we see and can observe back over to these kinetics, right? Because a lot of what we've been doing is saying, okay, we've got some kinetics, some reaction, blah, 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 let's do mass balance. And if we actually take an observation in the wild or in the lab or something, it's kind of neat to be able to say, oh, okay, here's how we get that K. And so that's anytime we're doing some disinfection experiment, there's a good likelihood we're doing one or the other, right? If we're studying a new technology, doing something like that, we're going to be taking a lot of observations like these. And it's all the same principles, it's just kind of flipped it backwards from what we've typically been doing. Now, you can consider the same problem to say, well, what if the pH was 7 and we saw the same activity? And then you have to do a bit of chemistry, say how much of this was HOCl. Then you might have to say, well, some of this action was OCl minus. I'll tell you right now, that doesn't play a big role because OCl minus is not very reactive comparatively. So then we would say, oh, okay, well, the chlorine must be even stronger because we had less amount of it. And the K would be different because our effective concentration of chlorine would be different, right? So there's a lot that can go into that. Maybe calculating the true amount of HOCl at pH 6 here would be a good exercise for you if you needed some practice on that. Okay, so this one, I probably won't give you something like this on the exam, just in case you're not equipped and adept with to do that on a graphing calculator. Something you probably could do, just if you kind of learned that. Clearly you can do it in Excel, but I'm not going to ask you to do data to K in that manner. Maybe some sort of interpretation of it. But. Okay, so moving on then, from kind of the chlorine or chemical disinfectants to ultraviolet light. So ultraviolet light, we call it that because it is beyond, in the energy sense, what we can see with our visible eyes, or with visible light with our eyes, what we can see with our eyes. So the visible range of light, if we look at light as a wave, the wavelength will be the distance between two peaks or two troughs. So this is our wavelength. We often write that as lambda. So lambda would be wavelength. And we're going to describe it for the purposes of visible and UV light almost always in nanometers. So the distance between these peaks, if we imagine that we shrink that distance, that means the wave is going a lot faster up and down. So that's technically higher energy. Now, a photon is both a wave and a particle, as we understand it. So it's a particle moving through space at the speed of light, obviously. That doesn't change. But these oscillations along the way can change. That's the change in color. So different colors have different wavelengths, and that corresponds to different amounts of energy. Turns out that blue has a lot more energy than red. And that's, in part, that's just how we perceive it. If you really want your brain to hurt, then you have to stop and think about, does your neighbor see the same, do they experience the different colors the same way as you do? Is blue the same blue to your neighbor? And of course, maybe some people are colorblind and that would be different, but it's something funny to think about, like, what I see as red, is that the same thing you see as red? How can we tell? How could we tell, right? It's a little bit of a mind puzzle. So our eyes then can't really see anything below 400 nanometers. That's kind of the cutoff for visible light. If we are exposed to something that's right next to it, we probably are seeing some of that. Usually there's a bit of a spectrum, and even the sensors in our eyes will catch some of the photons. It's not like precise, exact, but in general, we stop seeing light that's beyond that. So if we get to the violet range right around 400, then that's becoming more and more invisible to our eyes. So the sunlight, and I wish I should have pulled up that. I want to add a photo here because I have a nice photo from of the solar spectrum. Maybe I have it. Maybe I'll bring it in next time. Essentially, sunlight, we've got a lot of visible light, and then as it's getting into the UV region, it looks something like this, where we just have a tiny amount of UVB, which I'll explain in a moment, and a fair amount of UVA. So we just classify it that way. There's sort of ranges of light. Of course, we have a lot of visible light, and then it tails off. We get some infrared, but not as much as visible. Now, the sun actually puts out quite a lot of energy, even in the UV and the X-ray range. Our atmosphere, thankfully, absorbs a lot of that and takes that energy and converts it to heat and other stuff. So oxygen and ozone in the atmosphere in particular are really good at absorbing UV light. So any of this UVC stuff will be taken away from the sunlight unless we're out in space. So if we're out in space, then we actually have to be kind of worried about all of these things that are able to travel through a vacuum. In fact, if you do any really, really high-tech, like material science kind of stuff, you're going to probably end up using some vacuum instrumentation to use X-rays or things like that to detect really small stuff. Because visible light, what we can see with our eyes, has a limitation of this wavelength. You can't get resolution too much smaller than that wavelength to see something, see an object smaller than that. So if you use a light source that has very, very small wavelengths, you can see smaller things. And so because the small wavelength stuff like X-rays with wavelengths less than 100 nanometers, maybe even less than 10 nanometers, so, and so on, eventually you'll get to gamma rays and things like that. But to do that, the oxygen and the nitrogen probably in our atmosphere is just going to absorb all of the stuff, all the light. So you have to put it in a vacuum. So moral of the story is, if you're out in space, maybe you can disinfect your water with that light, but you don't want to be exposed to it directly. All right, so then more relevant to here and now, if you wanted a suntan, you mostly want UVA. It's going to trigger a lot of your cells to produce more pigments, because this stuff is getting to the point where it can be hazardous to you. The UVB is definitely hazardous. UVA can drive some oxidation reactions that produce oxidative stress. To some extent, it's good. It challenges your body and it helps you generate vitamin D and all that. But an overexposure then could be bad, especially if you are vulnerable to that oxidation. So UVB UVA kind of starts some of that. It's intense enough to do potentially a little bit of damage. And then as we go lower and lower, higher and higher energy, that becomes more and more hazardous. So the UVB stuff then is really what gives you the bad side of a sunburn. You can probably get a sunburn with UVA, but UVB is really where it's starting to stress out your cells, cause them to be damaged and or die, and start to get to the point where it might also be messing with your DNA a bit. UVC is the stuff that really does DNA damage directly, and that's what we use then for killing germs. That's where kind of we bring all that into our disinfection side of stuff. So UVC then we typically define around 200 nanometers to 280. When it comes to killing germs, this is the good stuff. So we'll say this is germicidal. So this here would be kind of solar at sea level. This is kind of the solar light we would receive through the atmosphere. So thankfully we don't get any germicidal light. They say, you know, the saying goes that sunlight's the best disinfectant. Well, sunlight without an atmosphere would be a very, very good disinfectant. With our atmosphere, thankfully, it's not so good. It can do it, it's just gonna take a lot longer. We'll talk about that more later today or maybe next time. So the UVA stuff, it could very slowly accomplish some disinfection, but if we wanna really make it work well, we're gonna use this stuff down in the UVC range. Okay, so that's kind of the broad spectrum of light, visible light, UV light, and kind of what we can do with that. So when we apply UV light for disinfection, we're going to do it in some manner that allows us to expose water directly and as intense as we can without losing too much light, and hopefully without too much issues with our bulbs themselves getting damaged or scuffed up or getting stuff accumulating there. And it actually becomes quite a challenge because there's not too many materials that are UV transparent, especially down at this level of ultraviolet light. So you'll notice a couple designs here. Often the middle one or the top one is the more common, where we have some bulb, some light bulb inside here. It's shining light, this UV light, and then we place that light in a protective sleeve. Now, as I mentioned, there's only a few materials that are transparent to UV light at that range. Glass, for example, will absorb it all. Most of the time, we actually like that in many cases. If you've ever driven in a car on a hot sunny day, you got your AC blasting, you ever think like, oh, I didn't get a sunburn, and I was in the sun the whole day. Well, the glass intentionally is absorbing the UVA light that would have given you a sunburn. So if you do the same thing, make the same road trip, but you have the window rolled down the whole time and you got your arm sitting there on the window, you might get a sunburn, right? But you never do when you're driving your car. Maybe a convertible would be different, right? So in this case, we have a protective sleeve to protect the bulb itself, but also to allow the light to go through. But this has to be a pretty fancy and expensive quartz. That's also fragile, unfortunately. So this is costly and fragile, which is not a great combination, especially when, as water's passing through it, especially if we're doing it with wastewater, but even with drinking water, there's gonna be some organics, maybe some minerals that start depositing. All of this light activity is probably causing some interesting chemistry too. It's gonna start accumulating junk on the surface. So then you have to take this out and clean off that surface in order to let the light pass through it again. And you have to do that in a way that is very careful and hopefully doesn't break the quartz. But you also have to scrape it. So it's a pretty difficult process, or a pretty big challenge to UV treatment generally. Of course, there are some innovations. There are a couple plastics, like this kind of it is an example, that they're not fully transparent, but they're close enough. And there are some innovations with some new light sources we'll talk a lot more about next time. Most of these are going to be mercury. So Hg is mercury, fluorescent lamps. So it turns out mercury has a very strong fluorescent signal just based on its electron configuration. If you excite an electron in mercury with the electricity, then it will give off a photon in the UVC range pretty effectively. And that's what we would call low pressure mercury, which is very common to use. That would be 254 nanometers. So that's a kind of common industry standard. There's another medium pressure. It's actually vaporized mercury. Medium pressure ones have a slightly different makeup, but it's also mostly in the UVC range. So that's kind of what we do, is we generate this light, we pass the water through, and we blast it. So a picture in a lab. Sometimes we use them in a bio lab to help keep the surfaces clean. Whoever's taking this photo, this one's not in my lab, but we have one very similar. There's this glass pane in front of it, and that glass will be absorbing all that UV. So it looks unsafe to have that scary germicidal, like it's going to damage your DNA, probably cause you to go blind, light right there. But that glass absorbs all the light. And I've tested this multiple times with a little lab radiometer thing. So, okay. So what does this exactly look like, and how does DNA absorb the light? Well, we can actually plot a graph of light absorption. You know, like different materials absorb different light. So my bottle here is absorbing a bunch of light, and so what we see remaining is blue light. So that usually means, unless it's like shining like fluorescence or something, unless it's creating the blue light, that what this means is it's actually absorbing most of the other stuff and not blue. So the blue is what we see reflected. So what light is absorbed by DNA in a manner that breaks the DNA? Well, that's this germicidal effectiveness curve here. So we can see anything from around 230 nanometers up at a peak at around 260, 265, and all the way up into what we called the UVB range, right? So we said this is kind of the UVB, and anything left of 280 was UVC, right? So germicidal then is meaning the DNA is directly being damaged by photons of this color, so to speak. And we see the two typical mercury lamps here. Just like indoor lighting, like these lamps here, they look like the old fluorescent ones, but pretty sure those are LEDs in there now. So just like indoor lighting, we have kind of converted from fluorescent lamps to LEDs. The industry is just starting to get LEDs in the range that are effective and becoming more efficient to power germicidal light with LEDs instead of these fluorescent lamps. So there are some new options, therefore, whereas these mercury lamps are kind of stuck to these peaks that we see. We can get some different peaks using LEDs. That's kind of neat, and that's a research topic of my own. But anything in this area is going to be effective, right? As we notice, when we start getting to the point where sunlight provides a little bit of this, it's really only a little bit of damage that it's doing, right? That's why we might be concerned if we are going to be exposed to a whole lot of intense sunlight, is because there is potential for direct DNA damage there just a bit, right? So that's one thing to kind of keep in mind. And by the way, if you ever do want some good sunlight, but you're kind of concerned about that, a good time to do it would be a little earlier in the day or a little later in the day, because then the sun's going through more atmosphere, more of that bad UV is being absorbed because it's going through more atmosphere. So if you went out today at 3:30 and spent 2 hours in the sun, that's going to be a lot less UVB than you would have if you spent from 2 hours from like 11 to 1. So just keep that in mind if you ever feel then, if you're ever going out and needing sunscreen, well, if you've only got 2 hours of strong daylight left, that's probably a time where you wouldn't need as much, right? Okay, so for the germs then, we want to give them as much absorbance, as much UVC as we can. And that's kind of what it looks like. The way we know that is because we've tested on different types of pathogens and viruses, things. So MS2, this is a virus that infects bacteria. We use it pretty often to say, as a example, as if it was a pathogen. It's not actually pathogenic, but we can see that how much light is being absorbed at different spots compared to the 254 nanometer spot. So it's normalized by this value, which is our typical UV light absorption. So we can test that for different organisms, and sure enough, DNA approximately has this shape in terms of the light absorption. So this also means that human DNA would be pretty similar, right? So if we were exposing ourselves to this stuff, that's not good. We can also take a look at how well it's inactivating light according to our wavelength. It's pretty much the same story. If we have light anywhere between 250 and 280, it's doing pretty well. Okay, so how does it work? Well, I like to say that UV damage for this germicidal effect is a lot like taking a zipper and you unzip it and then you put a little super glue between a couple of the spokes. What happens then when you try to then rezip it or unzip it, it's going to get stuck, right? So the way DNA works is it's a double-stranded thing, and all the biomolecular stuff happening, the machinery, it's constantly zipping and unzipping and making copies. So if you can take that super glue and gum up the system, preventing the zipping and unzipping, well, the cell itself might still live and function for a little while, but the fact that it can no longer unzip and zip its really important information coding machines means that it's not going to be able to replicate. It probably can't produce the proteins it needs for its typical functions. It's going to die with enough of this damage. So in particular, there's these base pairs and things from the DNA. Some of them are called thymine groups. And if you have two of those next to each other, you can get a thymine-thymine dimer. So it absorbs the UV light. It causes these two dimers to be reactive with one another. And that's the superglue sticking them together. And then when the enzyme from the cell comes through and tries to zip or unzip, it gets stuck there and doesn't know what to do. It just kind of kills the process. So that's the way UV damages DNA. It's not so destructive that it just like breaks everything all apart. So it's a little less drastic than chlorine, which is going to go and then oxidize everything. As you know, oxidation, burning things is oxidation. Chlorine, in some sense, is on a small scale, molecular scale, is just burning stuff up, oxidizing it, destroying things. UV is a little more particular with the damage that it's doing. Another way to look at that would be here with these thymine dimerized here, and it's just preventing that replication. Okay, so as we think about how to apply UV light, it's kind of good to think about what in the water might impact it. Mostly it's anything that could scatter light, that could shield the bacteria or virus from light, and to just generally know how far through the water the light will go. Now we could get pretty deep into all of that and define exactly how we quantify the UV doses. I'm not going to take you that far. That I don't think we really need to go that deep into it. But in general, it's just good to know the dose here is the amount of light that the solution experiences, right? So if we have large particles in there that could shield the bacteria and the viruses or scatter the light away, that's not so good. So we want to do our filtration type steps beforehand, before UV light, to have a nice clear water for it to transmit through. So that's kind of what's illustrated here. If we have a UV lamp, but then a particle, it's not going through, right? So there's a problem if we have a bunch of particles. It could also be a particle if we, it could be a problem if we have a bunch of molecules that just absorb the light. As if I put some dye, maybe some, I don't know, Kool-Aid or something, or tea. Those molecules that are absorbing light, maybe there are some that we can't see that are just organic matter from soil or something, absorb UV light pretty well. So if we have a lot of that, it's a similar problem. The light's just simply not traveling so far through it. So if those are, if those are the problems or the issues, then we have less effectiveness of our UV light. So in general, we design it, again, at one of the cleanest spots in our treatment so that it can have the most effect. And just like we would with chlorine. Now, when we go to describe this with, mathematical terms, we're using the Beer-Lambert law. You've probably used this or seen this in general chemistry at some point. We don't need to worry too much about it, but if you're curious, this is the precise way to describe it, where we can have some change in intensity. So we'll take the log of the intensity that has been transmitted divided by what we started with, and we can say that's equal to, an equation that says the molar absorptivity, this gamma thing, times for that given wavelength, times the concentration of whatever's doing that absorbing. This is just to say, if you have really, really weak sauce tea, light's going to go through it, and you're going to see just a faint little brown. If you have a really strong tea, you're going to see, okay, this is, let's say iced tea or something. You're almost getting no light through. You can see that light's coming through, but it's, it's very dark brown liquid, right? That's the scientific way of saying that. It's kind of obvious. The more you have of the stuff, the more light's going to absorb, right? So that, you've seen that, you've even used that in practice in your daily lives. So I mentioned just a moment ago for different organic matters. So this is, don't remember what this one is, but this one's the Suwannee River Natural Organic Matter. It's a river in Georgia that happens to have a very characteristic tea-like brown stain organic material, and it's people have just harvested organic matter from that because it's very consistent, and the science studies of organic matter in rivers have used that as a standard for many years. So this is just natural organic matter. And what we see, kind of elaborating on the potential problem for organic matter to absorb light, is we see that this stuff, it's not really absorbing too much visible light. Maybe we see a hint of brownness or something if we have got a lot of it. But even a small amount of it will absorb a fair amount of UV light, of the UVC in particular. So these are just mixtures of all sorts of molecules. So molecules tend to absorb more UV light than visible light. That's why it's hard to find something that's transmittent for the UVC. So as we can see, if this is absorbing all the light, that's going to take away the light so that our DNA is not going to absorb it. That's the problem. And if we have a lot of it, or if we're taking our light through a really deep segment of water, then it's not going to go so far through it. That's kind of the point. So generally then we design our systems to have a short depth for the light to penetrate through, so that we know we have a lot of light exposure, and we hopefully don't have too much of this. One other thing we might be able to do with the new LEDs is to shift, even just a small shift from here to here might make a nice difference in terms of how much light is being absorbed by this unwanted, annoying stuff. The natural organic matter, if there's not too much of it, it's just an annoyance. In fact, you probably can't taste it if there's not much of it. Probably not doing much of anything except for causing some small troubles for things like this. So if we can shift our light just a little bit, still have good germicidal effectiveness, maybe that's some advantage there. Okay, so how do we quantify our rate constants for UV light? All of this is just going to basically say it's the same as we did with the chemistry, except instead of the, let me back up a step. The same as we did with the chemical disinfectants, except that instead of a concentration of a chemical, we have some amount of light exposure. And how do we quantify light exposure? It's going to be, we'll take some area, put it under a light, and say how many photons are hitting there per area per time. So it's going to be some dose of light, and maybe we report it as energy. So this rate equation then is going to be almost the same as when we said dN dt equals negative k times c to the n power times t, except now it's going to be negative k times the UV dose times t. Okay? So that's going to be the difference. It's just a matter of, excuse me, I didn't mean to put t there. Should be n. Okay. So the difference here is just that we're putting in a different feature for what's doing the action, right? And presumably we're going to keep that constant. Okay, so when we take a look at our rate equation, the rate at which n is changing for a given wavelength is minus n to the 1 power, so it's first order, depends on how many are there, times this uppercase lambda, that's going to be our coefficient, that's going to be our k basically, times i's intensity, that's going to be kind of that c to the n power that we use, that's the concentration, so to speak. It's going to be the intensity of light at that wavelength. All that's our dN dt equation. So each of these parameters are written out, but really we don't even need to know too much. We just need to know that it's going to be some intensity, that light intensity, and a constant for how vulnerable a given pathogen is to that type of light. Okay, so very much parallel to the chemical concentration. So the dosage then is going to be, the total dosage is intensity times time. So if we're doing UV dosing, that's giving some amount of intensity of light for some period of time. Just like chemical dosing would be, so in the chemical way, that would be the concentration times time for something like chlorine, right? So if we're describing a dose, this is how much time that the bacteria, the water, has been exposed to this thing that's killing the bacteria or the pathogen. Okay. Does that make sense? So we can take a look at things like flux of light and things like that. At the end of the day, we are really just dealing with how much light has the water received, and for over what time period. That's the deal. You should pretty much be equipped based on all the other mass balance stuff we've done to deal with this. It's, like I said, just like the chemical disinfectants. It's just a matter of understanding how to put that rate equation together to insert that into your mass balance. So we could put this in batch, we could put this in a CSTR, whatever design we desire. Okay, just to elaborate just a tiny bit more on that dosage concept, to make it especially clear, we could say this is the intensity on average for the light times the time. Okay, that's just all spelled out here. And we could also take a look at the units here. Overall, we might call this dosage fluence. If you want to be technical about it, that's the amount of light per area per time. And you'll notice this dosage then would be some energy of light per area. Now, joules is actually watts per time, or watts times time. So that's the energy times time, giving you the total energy that has been received. So that's kind of how we might express it. So if the dose is millijoules per centimeter squared, the intensity itself with a snapshot would be like milliwatts per centimeter squared. We give that some amount of time, and there we go. So we can describe those units whatever way is needed for our system. Okay. Any questions, concerns about that? All right, I think that's okay. Got one more problem for you here, and we'll end on this. So, example for UV light, just to make sure that we kind of understand what's going on. I think I've probably put this on an exam before, so you can kind of see what this might look like. So we have a company designing a solar-driven portable water disinfection system to be used by the military. The system is simply an inlet tube, a pump, a well-mixed chamber, and an outlet tube. The water is pumped continuously into the chamber where it is irradiated with UV light before exiting through the outlet tube into a collection vessel. The disinfection rate constant for the UV light is 7.8 per second, and the bacterial count in the water must be reduced by 99.9%. Because the military needs the unit for a backpack, or to fit in a backpack, they require that the unit's chamber be no larger than 2 liters. So the question is, how much water will the system be able to produce during 10 hours of sunlight? So go ahead and see if you can tackle that problem. Would suggest sketching it out first and kind of scheming what kind of a mass balance approach is required there. Right, so hopefully you had a chance to set it up and get working on it. I basically did a whole bunch of setup here so you can kind of see, how your efforts have related and maybe were guided by this stuff. So I started with a drawing, right? We have some container, it's well mixed, we were told. It has a pipe coming in and a pipe going out, or tube. It's got some volume that we know, we could even write that, that's 2 liters. And we can write that there's some flow going through with some influent concentration of bacteria and some flow leaving with the effluent concentration of bacteria. So pretty typical CSTR setup then, and we can assume steady state because we're not given any information about kind of like how are things changing over time. We just need to run it for a certain amount of time, kind of make that assumption. So that means our mass balance is no net accumulation. So 0 for that term is equal to what's coming in minus what's going out minus whatever's being killed by the reaction, right, the UV light. And then when we think about that reaction term, here's where it could get kind of confusing. dN/dt, we know we can simplify it down to negative k star times n, right? That should be what it simplifies to. And we could say, okay, well, that k star should be some function of that intensity times the specific lethality k thing, which we could also write as an uppercase lambda. Turns out if we take a look at the units, we're given units for our for the disinfection rate constant here. Let me find my cursor. As per time. That means what we're given is basically the k star. So we actually, in this problem, we don't even need to go to the level of figuring out what's going on with this intensity stuff. So it's an option if we need to. We know we can break that k star into an intensity and a specific lethality thing, like we did in the problem at the start of class, but we didn't need to, right? And so it's okay that we're not given any information about intensity for the light. It's just we're given that it's functioning some effect, right? So just be looking out for that, right? You could have both, or you could just have the summary one. In this case, we just have that summary one. This type of problem could fool you because it's easier than you thought, right? So just try to be attentive to what's going on there. So we'll just leave it as k star, and then this is just a very standard mass balance system on a CSTR. The only difference is we need to solve for the total volume after 10 hours, meaning we should probably solve for Q, which we don't often solve for, and then multiply that Q by 10 hours, and there we go. Okay, so that's going to be the approach. So let's go ahead and get Q by itself. We'll say Q times N naught minus N. It's going to be equal to, I just add the VK star N to both sides. Q will be equal to V K star times N divided by N naught minus N. Now, the N's are going to be a little annoying. We'd like it for it to be in some form of N over N naught or something like that. So I think I'll divide the top and the bottom here by N and see what happens. We could have also just solved it for N over N naught in the first place and then rearranged for Q. That would also work, but just happen to be doing it this way. So let's say that's going to be V K star times N over N divided by N naught over N minus 1. So if we need 99.9% removal, that means our N over N naught is 0.001. If we invert that, that should be 1,000. So this is going to be equal to VK star divided by 1,000 minus 1. Okay, so that'll get us our flow rate, but that's going to be in liters for the volume and per second for the K. So that'll give us liters per second. Then we need to multiply that by 10 hours, convert the seconds to hours, and find our number. So I'll do that real quick with you here. We'll say The V was 2 liters. K was 7.8. per second. And Q will be equal to that volume times K divided by 999. Yep. That's going to be in liters per second. And so I'll say, we'll take that and go from seconds to hours. So we need to say times 60 for minutes times 60 more for hours. Liters per hour. That means our total volume treated will be that times 10 hours. So 562 hours. We'll go ahead and put this in first. Q was 56.2 liters per hour. So 562, right? Yeah. Okay, does that make sense? All right, so just, use this as a reminder that what really we're doing with these problems is understanding what exactly it's asking for and how we're going to get it. The fact that we're using UV light is not so different than anything else. If anything, we just have to have that intensity and a specific rate constant, just like in the chlorine example, we needed the chlorine concentration and a specific K for that. All right, so with that, we'll see you on Thursday.